Welcome to True Projects. In this video, we are going to explain about the project title Ensemble-based dimensionality reduction for intrusion detection using random forest and wireless networks. Introduction. The project is primarily focused on improving the ability to identify and counter potential intrusions in wireless networks. It aims to achieve this by utilizing a combination of ensemble techniques and dimensionality reduction methods. The goal is to increase accuracy and strengthen the ability to identify and mitigate security threats within these networks, thereby enhancing overall security. Two specific datasets, NSL-KDD and UNSW-NB15, are being employed in this project. These datasets serve as the foundational source for the development and analysis of models aimed at detecting and preventing intrusions effectively within wireless networks. By utilizing these datasets, the project ensures a robust evaluation and development environment for intrusion detection models. Various techniques such as correlation-based feature selection, partial least squares, principal component analysis, linear discriminant analysis with recursive feature elimination, and BLDA, LDA with RFE are being implemented. These techniques aim to streamline the features used for model training by selecting the most relevant ones. This process enhances model efficiency by reducing computational complexity and noise in the data, ultimately improving the model's ability to detect intrusions accurately. Ensemble methods are being introduced to combine the predictions from multiple individual models. This amalgamation of predictions from different models aim to boost overall accuracy and resilience against intrusion attempts. By leveraging the strengths of multiple models, this approach can often yield more accurate and robust intrusion detection systems compared to individual models alone. Objective. The primary aim of the project is to enhance the capability of detecting and preventing potential intrusions within wireless networks. This goal is pursued through the adoption of advanced methodologies which encompass a range of techniques and models geared towards improving the accuracy and efficiency of intrusion detection systems. Ensemble techniques are employed to harness the collective strength of multiple models. By combining various models, the project seeks to achieve heightened accuracy and reliability in detecting intrusions within the network. This approach is known to often outperform individual models by leveraging diverse perspectives and learning patterns. The project proposes a hybrid approach for intrusion detection in networks. This method involves the utilization of blended linear discriminant analysis (BLDA) for feature selection and the random forest classifier for the actual intrusion detection process. BLDA serves to refine feature selection, while the random forest classifier is used to identify intrusions within the network. The proposed method, which combines BLDA for feature selection and random forest classifier, is compared with classical feature selection schemes like linear discriminant analysis (LDA), principal component analysis (PCA), and partial least squares (PLS). The comparison demonstrates that the ensemble-based method significantly enhances intrusion detection system performance compared to these traditional techniques. The overarching aim of the project is to reinforce the resilience of intrusion detection models against evolving intrusion tactics and network vulnerabilities. This is achieved through a strategic combination of ensemble strategies which amalgamate multiple models and feature reduction approaches. The objective is to create more robust intrusion detection systems that can adapt and respond effectively to dynamic threats in network environments. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, backend framework is Jupyter Notebook, database is SQLite 3. Front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This initial step involves importing necessary libraries and packages in the Python environment that are essential for data manipulation, visualization, machine learning, and other functionalities required for the project. Commonly used libraries like Pandas, NumPy, Matplotlib, Seaborn, and scikit-learn are imported at this stage. Exploring the dataset, NSL-KDD, and UNSW-NB15. This phase involves loading and examining the NSL-KDD and UNSW-NB15 datasets. Exploratory data analysis (EDA) techniques are applied to understand the structure, features, and characteristics of the data. This step helps in gaining insights into the data before proceeding with further analysis and processing. Data processing using Pandas data frame. The data is structured into a suitable format for analysis and modeling. This involves cleaning the data, handling missing values, and transforming the dataset as needed for subsequent steps. Dropping unwanted columns that do not contribute significantly to the analysis helps in reducing noise and improving efficiency. Visualization using Seaborn and Matplotlib. Visualizations using Seaborn and Matplotlib aid in understanding the dataset's distribution, patterns, correlations, and trends. Graphical representations such as histograms, box plots, scatter plots, and heat maps are created to visualize relationships between variables and identify potential insights. Label encoding using label encoder. Categorical variables often need to be converted into numerical format for machine learning models. Label encoding using tools like scikit-learn's label encoder is applied to convert categorical data into numerical representations, making it suitable for model training. Feature selection. Various feature selection methods are employed to identify the most relevant and informative features for model training. These techniques include correlation-based feature selection. Selects features based on their correlation with the target variables. PLS, partial least squares, reduces feature dimensions by capturing relationships between input and output variables. PCA, principal component analysis, reduces data dimensions by transforming correlated variables into uncorrelated components. LDA with RFE, linear discriminant analysis with recursive feature elimination, utilizes LDA with a recursive elimination process to select the most significant features. BLDA, LDA with RFE combined with PLS, a novel ensemble technique combining LDA with RFE and PLS for enhanced feature selection. Splitting the data to X and Y for machine learning. This step involves segregating the dataset into two parts, X features. This subset contains the independent variables or features that will be used to predict the target variable, intrusion or non-intrusion. Y, which is the target, this subset holds the target variable or label that the model aims to predict based on the features. In intrusion detection, this represents whether a network activity is normal or malicious. Building the model. In this phase, the structure and architecture of the machine learning model are established. The chosen model, random forest in this case, is defined with its parameters and configurations. The model building process involves selecting appropriate hyperparameters and preparing the model for training. Training the model. Once the model is set up, it is trained using the label dataset. The model learns patterns and relationship between features and the target variable, intrusion or non-intrusion, during this training phase. The goal is to create a model that accurately predicts intrusion in wireless networks based on the provided data. Flask framework with SQLite for sign-up and sign-in. This involves setting up a web application using Flask, a Python web framework, and integrating a SQLite database for user authentication, allowing users to sign up and sign in securely. This provides a platform for user interaction and input. User gives input as feature values. Users input the required feature values relevant to network activities into the system. These inputs serve as the basis for predicting whether the network activity is an intrusion or not. The given input is pre-processed for prediction. The input provided by the user undergoes pre-processing steps similar to the initial data processing phase. This includes data cleaning, formatting, and encoding to prepare it for prediction by the trained model. Trained model is used for prediction. The pre-processed user input is fed into the trained model to make predictions about whether the inputted network activity is considered an intrusion or not. The model utilizes its learned patterns and relationships to make this prediction. Final outcome is displayed through front end. The final prediction outcome, indicating whether the inputted network activity is classified as an intrusion or non-intrusion, is displayed to the user through the front end of the web application. This completes the cycle of user interaction and predicting using the machine learning model. In this project, we have utilized dimensionality reduction methods. These techniques are likely chosen in the project due to their ability to select the most informative features, reduce the dataset's dimensionality, and enhance the performance of machine learning models like random forest and intrusion detection system. Each technique addresses specific aspect of feature relevance, relationships, and reduction to optimize the model's predictive accuracy and generalization. We have used the following methods. The first one is correlation based feature selection. Correlation based feature selection selects features based on the correlation with the target variable. It identifies and retains the most relevant features that have a strong correlation with the outcome. PLS, that is partial least squares. PLS is a dimensionality reduction technique that captures relationship between input and output variables. It reduces feature dimensions by creating new features that are linear combinations of the original ones, aiming to explain both input and output variance. PCA, Principal Component Analysis. PCA transforms correlated variables into a smaller set of uncorrelated components, principal components. It aims to capture the maximum variance in the data with fewer dimensions, making it easier to analyze while retaining most of the information. LDA, Linear Discriminant Analysis. LDA is a technique used for dimensionality reduction and classification. It seeks to find a linear combination of features that characterizes or separates classes in the data by maximizing the distance between class means and minimizing the variance within each class. BLDA, LDA with RFE combined with PLS. BLDA is an ensemble technique that combines linear discriminant analysis LDA with recursive feature elimination RFE and partial least squares PLS. It aims to leverage the strengths of both LDA with feature elimination and PLS for more refined feature selection. Algorithms used in the project are random forest. Random forest is an ensemble learning method that constructs multiple decision trees during training and merges the predictions to improve accuracy and prevent overfitting. It's robust and effective for classification tasks, including intrusion detection. Voting classifier. The voting classifier combines multiple individual classifiers prediction. In this case, it combines random forest with AdaBoost, another ensemble learning method. The idea is to merge the predictions of random forest and AdaBoost to achieve higher accuracy and robustness in intrusion detection. We have utilized these dimensionality reduction methods along with these algorithms. These techniques and algorithms collectively form a comprehensive approach to feature selection and model building for intrusion detection. They aim to streamline feature selection, reduce dimensionality, and leverage ensemble methods to create more accurate and resilient intrusion detection systems in wireless networks. As an extension, we applied ensemble methods combining the predictions of multiple individual models to produce a more robust and accurate final prediction. Comparison graphs. Comparison graph offer a visual breakdown of how a model performs across essential evaluation metrics. In this project, we have utilized NSL-KDD dataset. NSL-KDD is a refined version of the KDD Cup 99 dataset. It addresses some limitations of the original dataset, such as redundancy and irrelevant records. NSL-KDD offers a more balanced distribution between normal and attack instances, ensuring a more realistic representation of real-world network traffic. It's commonly used for developing and benchmarking intrusion detection systems due to its enhanced quality and reduced redundancy. This is the accuracy comparison graph. On the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is a precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. Here on the x-axis we have FN score, and on the y-axis we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Comparison graphs of UNSW NB15 dataset. In this project, we have also utilized UNSW NB15 dataset. UNSW NB15 dataset is a contemporary dataset curated for network intrusion detection research. It was created based on real-world traffic captured from a representative network environment. This dataset contains a diverse set of attacks, including DOS, shell code, among others. UNSW NB15 is notable for its diversity, reflecting modern network behaviors and challenges, making it suitable for training and evaluating intrusion detection models in current network environments. Models are compared with the parameters accuracy, precision, recall, and FN score. Execution. To execute this project, first we need to open the code folder which contains the source code files. Folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are model files which contain algorithm information which will be loaded into the project code during runtime. These are notebook.ipynb file. These are Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. So here I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, this localhost, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flash framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered. So click on sign in. So here we need to enter the username and the password which we have created and then click on login. We have logged in successfully. We can execute the project using different data sets. Click on prediction link. Here we can see the data sets NSL-KDD and UNSW-NB15. First, we will execute the project with NSL-KDD. So click on it. So here we need to enter these parameters to predict whether attack is detected or not. Before entering the parameters, let us understand the parameters. So the first one is service, indicates the type of service requested or utilized. Flag represents the status of the connection. SRC bytes, that is source bytes, number of bytes transmitted from the source. DST bytes, that is destination bytes, number of bytes transmitted to the destination. Count, number of connections or instances observed. Error rate, rate of connections with SYN errors. Same SRV rate, rate of connections to the same service. Different SRV rate, rate of connections to different services. DST host SRV count, count of services for a destination host. DST host same SRV rate, rate of connections with the same service to a destination host. DST host different SRV rate, rate of connections with different services to a destination host. DST host error rate, rate of connections with SYN errors to a destination host. Now we will enter the parameters. So I'm entering the parameters. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is DDoS, that is distributed denial of service. Now we will enter another set of parameters and check whether attack is detected or not. So I'm entering another set of parameters now. So here I have entered the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is probe. Now we will enter another set of parameters. So I'm entering the parameters now. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is R2L. Now we will enter some more parameters and check whether attack is detected or not. So I'm entering another set of parameters. So here I have entered all the parameters. Now click on predict button. Here we can see we got the result. There is no attack detected. It is normal. In this way, by entering the parameters, we can predict whether attack is detected or not. And if attack is detected, what kind of attack is detected? DDoS, R2L, probe, or normal. Now again, click on prediction link. We will execute with another data set, that is UNSW-NB15. So click on UNSW-NB15. So here, these are the parameters. After entering the parameters, we can predict whether attack is detected or not. Before entering the parameters, let us understand the parameters. So the first parameter is duration, time duration of the connection. Protocol, protocol is used for the connection, example TCP, UDP. S bytes, that is source bytes, total number of source bytes sent in the connection. Rate, transfer rate, data transfer rate during the connection. S load, that is source load, average data transfer rate in the source to the destination direction. S loss, that is source loss, number of packets lost in the source to destination direction. S inc packet, that is source inter packet time, average time between packets sent in the connection. S mean, that is source mean, mean of the packet sizes transmitted from source to destination. CD SRV SRC, connection tracking service source, connection tracking state for the source. CT stage TTL, connection tracking state time to live TTL associated with the connection state. CT DST SRC LTM, connection tracking destination source last time made, number of connections of the same source to the same destination. CT SRV DST, connection tracking service destination, connection state for the service destination. Now we will enter the parameters. So I'm entering the parameters. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Now we will enter another set of parameters and check whether attack is detected or not. So I'm entering the parameters. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. In this way, by entering the parameters, we can predict whether attack is detected or not. Now click on sign out button. The conclusion of the project is the project introduces a hybrid approach using blended linear discriminant analysis BLDA for feature selection and the random forest classifier for intrusion detection in wireless networks. This method exhibits significant enhancement in the intrusion detection system IDS performance. BLDA refines feature selection while random forest excels in accurately identifying intrusions. The project effectively utilizes the BLDA approach to select the most relevant features from the dataset. By doing so, it reduces the dataset's dimensionality while preserving crucial information. This reduction leads to improved accuracy and performance of the IDS by focusing on the most informative features. The random forest classifier, combined with the chosen feature selection approach, proves to be highly effective in detecting intrusions within the network. By leveraging the selected features, the classifier robustly identifies and prevents attacks, ensuring a secure network environment. The proposed IDS isn't limited to a specific dataset. It demonstrates its efficacy across benchmark datasets like NSL-KDD and UNSW NB15. This versatility is crucial, showcasing high accuracy rates across different datasets, underscoring the IDS effectiveness and generalizability.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.